Anyway, it's great to be here. Yeah, and I'm going to talk about some work we've done on surrogate modeling of bridges in a highway network. It's part of kind of a broader vision of trying to do high-resolution models of any type into a regional analysis. Follows nicely, Brett, what we heard earlier about surrogate geotech models. I'd like to acknowledge Carmen Andrade, who's here somewhere, who did a lot of the work along with Mia Lockhead, another student at Stanford, and we had other contributors. This is part of a peer project, but also some work that we're using a lot of the tools and helping develop those tools as part of the Sim Center. So the question is, you want to do this regional analyses. We'd like to model bridges with a lot of detail to characterize the individuality of each one within a regional simulation. How do we do that? Well, having something that's scalable that we can operate on quickly, doing multiple realizations over a large network with many hundreds or thousands of bridges, while maintaining kind of high fidelity of the order you would get if you did, say, a detailed structural analysis model of each of the bridges and their foundation. So that's kind of sort of the goal we're after. So the project scope is we're going to be looking at regional models, and first kind of take you through a path of if you were doing a HAZIS type analysis. And here we are using some of the tools of the Sim Center. We heard of the R2D tool earlier that does some of these regional analyses. Also, we have a library called Pelican that has all of the HAZIS bridge fragility functions in. So we could take it through that and do realizations of earthquakes, simulate damage with HAZIS, and see what the outcome is. But then also to look at a higher resolution alternate, which is to take a path through these surrogate models and predicting damage based on those, and then start by, at least in this project, doing some comparisons between those two routes. Different types of surrogate models that are out there. You could think of some sort of a linear type or some type of regression model, but we'll be looking at two types. One's called a Gaussian process model. This is actually built into a Sim Center tool called QuoFem. And then another one that we've been working on the development of, probabilistic learning on manifolds. So those are two types of kind of statistical machine learning models that we'll take a look at. Focus on the probabilistic learning on manifolds, because that's one that actually I've reported on previously. Started with working with Sanjay Govinji here at Berkeley when he was directing the Sim Center. We put together this kind of statistical model that to kind of characterize the responsive structures. The nice thing is it doesn't rely on fitting things to any kind of Gaussian or other distributions. It kind of captures the inherent correlation between different parameters in the response of a structure. So what we've done more recently is to take that model to the next step and to go fast, to go slow, to go through a kind of a meticulous process of training this model and validating it and kind of walking through the steps, and we applied that to the bridge model that we're going to apply in the regional simulation. So I'm going to talk a little bit about that process. A lot of the details are in these two papers that are shown here. You know, the first one is when you want to train a surrogate model, you need a bunch of training data. So in our case, we'd be looking at developing a number of bridge models that are representative of bridges of the type, say, here in California, with different parameters and so forth, and kind of semi-automating their design so that you could populate a lot of, or develop a lot of models of these bridges with variability in certain structural characteristics and so forth, and then eventually semi-automate the process of creating open seas models. So we focused for this study first on kind of pre-1971 two-span single bridge concrete bridges. There was some work done previously, Reggie DeRose and Jamie Pageant working on the next generation fragility function, a project that Caltrans Cliff Robley kicked off some years ago, where they collected a lot of statistics of the characteristics of reinforcing bar strength, column sizes, axial load ratios, and so forth. That's kind of built into this training data that we're developing. And then out of that, then we came up with 600 different designs representative of this body of bridges, with different design parameters. A few of the key ones, and these ones will index when we're making predictions on the surrogate model, looking, say, at column slenderness, pier slenderness, axial load ratio, longitudinal bar, rebar area, and Fy to get the strength of the structure. The next would be, so we have that 600 training data. We want to then subject them to ground motions, and here we're going to do incremental dynamic analyses with a set of ground motions applied to those 600 models. But for the input ground motions, we want to characterize them course, in terms of kind of indices, intensity measures. So spectral acceleration, of course, that's what we start with. Next, picking up spectral shape, and for this we use an index called SA ratio. It's kind of related to SA average, kind of distinguishing between the different spectral shape, which will influence kind of higher mode effects and structural softening as you get towards collapse, and also significant durations. So those will be the things that we're distinguishing in the ground motions we're using for the training. And then to do these IDA analyses, we've gone in through the peer database and got what we call a grid of ground motions. That is, picking an assortment of ground motions with a range of SA ratios and a range of durations, so a large suite that we pass through these training models, so we have the statistics to kind of cover the whole range of ground motion characteristics that could be encountered at different sites. And then the process goes through of sort of training the model, and I won't go through the details of that, they're in those papers, but then I'd like to talk about when we want to, once we have these models trained, how would we apply them to a regional simulation? So the first thing you'd imagine is for each bridge location that you could identify its structural design characteristics, where you could discern those from different features. One of the challenges in these models is taking the available databases, say the NBI, National Bridge Inventory, and then inferring the structural features, or maybe you could use some image recognition to hone in on them more carefully. And then the ground motion characteristics, those are a little bit easier through all of the ground motion models we have and PSHA tools to kind of characterize the intensity, spectral shape, and duration. And then through the surrogate models, calculate the response, looking at the probabilities of collapse, and then looking at, for the non-collapse cases, what are some demand parameters, looking at curvature or curvature ductilities in the columns. Also, the open seas model we're using is one where we developed a model to pick up reinforcing bar fracture, so that's another kind of outcome in our open seas models that we're then training the surrogate model on. Now, one of the things, once we get the model trained, to validate it, what we did is we took a suite of 9 particular bridges, or 9 particular cases, I should say. These are 3 bridges, so we'll pick 3 different bridge locations with different features, say varying the axial load ratio, the slenderness, and so forth. And what you see in the graphics on the lower left is kind of these individual bridges, where they sit relative to the population of the overall training data set. And then subject these to different suites of ground motions. And here we use a multi-stripe analysis characterizing the hazard at 3 specific sites that have different duration, ground motion duration, different spectral shape. And then for each of those to develop through this multi-stripe analysis, another set of 600 data points per bridge, which is kind of like the ground truth that we'll use for this validation exercise. So this is an example of the multi-stripe analysis data that we would get. So if you look at the right side of the picture here, for example, it's looking at the curvature demands, if you will, under different intensities. We have these 10 different stripes that are shown here. And you see as you go higher and higher, you get larger curvatures. Some of them we're declaring have been collapsed. And then in the plots on the left, you could see that for the non-collapse cases, we're getting those statistical distributions of the maximum curvature or the fracture index as a function of increasing ground motion intensity. And these, again, for the 9 cases we're looking at, these would be unique to each of those, serving as ground truth. And then the question is, can our surrogate model predict something comparable to this? So the comparisons we did is to run the surrogate model against this validation data, and just a snapshot of the images or the results is, say, looking at the collapse performance shown down below, and just to kind of, we'll look at a couple of these to characterize what we're seeing. So we're looking at the spectral acceleration versus probability of collapse. The blue curve is the overall training data set that we started with, and then the green and the yellow curve, one is the validation data and the other is the plum. And the fact, and here you see the plum surrogate model is doing a good job of picking up that collapse fragility curve. And then we repeated that for other sites where we have different axial load ratios, different slenderness and so forth, where the points are moving around. And the question is, can the surrogate model be picking up those effects? Now, one of the scalars to kind of measure are these good fits or not is if we take those collapse fragilities and if we integrate them with the hazard curve, the seismic hazard curve for each site, and get a mean annual frequency of collapse. So that's what's shown in the table up above, comparing, again, the multi-stripe analysis to our plum data, and you see generally good agreement between the two. That would be on, say, the collapse performance. Next, if we look at the engineering demand parameters for the non-collapse cases, Now here we could look at these at each of the stripes, not just at the collapse point. So from lower ground motion intensities, more frequent return periods, to more extreme cases for all of the 3 different bridges that we looked at the different site locations that are shown there. And I won't go through all the details, but suffice it to say we wouldn't be presenting it if we didn't think we did a good job, that statistically our predictions for the estimates of this maximum curvature and fracture index are in pretty close agreement, like within statistical bounds of that multi-stripe. So it convinces us that we've kind of done a good job of training this surrogate model. Okay, so now I'd like to go back and look at how we would apply it to these regional simulations and compare it to some of the HAZIS results. Okay, so first we'll look at the HAZIS assessment. Here we're making use of a couple other tools that have been developed in the Sim Center. One is called Braille's++. This helps develop inventory data. It could be inventory data on buildings from the National Structures Inventory in other cases, or for bridges, it's connected to the National Bridge Inventory. So in this, if you pull it into the Braille's tool and you identify the region you want, it will quickly pull up the information out from the National Bridge Inventory and identify it with the bridges that are shown in the region. We also have under this tool suite a SimCenter earthquake scenario tool that goes into the USGS OpenSHA and USURF3, where you could then pick out a fault rupture. In this case, we picked out the Hayward fault rupture that was used for the Haywired scenario a few years back, and then run a PSHA type to do multiple realizations of correlated ground motion intensities over the region. So we did 500 realizations from this one fault rupture, and from those we'll get spectral acceleration at 1 second. We're going to get the spectral shape factor, or the SA ratio, and we'll also get duration for each location. So we have a map of the bridge inventory, and we have a map of the seismic hazards. We could then pass it through, in this case, the HAZIS fragility functions. And for those 500 realizations, we repeat the process for each bridge at each location. And you can see plots of what's shown here say the most likely damage state you're going to get out of the 500 realizations. Each of those is coming from, I think we're familiar with these fragility or damage functions, if you will, spectral acceleration at 1 second versus the different damage states. And then what you see at the right, and I'd like to point out some trends you see, is that if a site has low seismic hazard, that you tend to find, like the case that's shown in the lower right, you tend to find low damage. On the flip side, when you have very high shaking, it's going to be a lot of high damage states. When you're intermediate, you tend to find a pretty big spread of different damage states, and sometimes it's kind of bimodal, like even for the cases that are in the middle, and that's a function of these fragility functions. If you imagine at a middle value of spectral acceleration, if you read up, and if you're taking random picks off of those fragility models, you'll tend to get a bimodal distribution, just because there's more probability in being complete damage or no damage as compared to those intermediate states. Okay, so that was for the HAZIS. Then we went through the 2 surrogate models, the Gaussian process and the Plum model I described. So we're starting with the same input. I should mention for the HAZIS, we're only making use of spectral acceleration at the first period. As we use these surrogate models, we're making use of both the SA ratio, spectral shape, and duration. So we could go in and estimate structural collapse, estimate the curvature ductility demands using either one of these surrogate models. And then we could pass that through. In this case, we use the Caltrans column damage thresholds. So another set of fragility functions, but these are ones where you have the curvature demand as the input, predicting different damage states. So it's a similar outcome. And then this, we could then compare what are the damage states predicted through this method to the ones that we would have gotten through HAZIS. And presumably this method should be better at discerning differences in the seismic hazards, a spectral shape or duration, or the bridge features themselves than with the HAZIS functions. Just wanted to give a glimpse inside of the simulations that we would do with these. We would first kind of characterize the ground motion parameters at the site and the structural parameters we're looking for, and then statistically pull out those sets through these surrogate models, the Gaussian process or the probabilistic learning on manifolds. And what's shown on the right, if we compare these 2 surrogate models against themselves, and we've trained kind of both of those, we find, say, for example, for one kind of return period ground shaking at one site, we're getting similar curvature demands. So that's kind of reassuring to us that apart from the validation we did before, the two models are giving somewhat similar results. And again, like I say, we're relying on this Caltrans column damage threshold fragility model to take these structural results and get into damage performance states. Now, I mention this because this is another area where judgment comes into the picture. And in fact, Caltrans has been working on their next generation fragility functions. This is where, for example, this sort of fragility model could be updated on top of these surrogate models for getting better predictions of damage. But if we step back and we look at the cases that we've run and we compare Haas's damage functions to the surrogate models, see the Gaussian processor Plum, we find on average when you look over the whole region, you get about the same damage, but there are differences and maybe more distinguishing features when you go through the surrogate modeling approach. Now, we'd want to mention that something that came up as we were looking at this data, if you think about what's the final result we want to get out of this regional simulation of bridge damage. Of course, you'd like to know how many bridges are damaged, what kind of repairs need to be done. But if you're a traffic modeler and if you're looking at critical links of transportation links after an earthquake, or you're looking at recovery routes and so forth, it's not just damage to the bridge, it's closure of a road. So one of the things that was intriguing to us here, this is from, again, it's one scenario we're doing, this one Hayward scenario, 500 realizations. For 3 of those realizations, what's shown here is a snapshot of different bridge damage states you'd get for the different ground motions that's coming out of these 500 realizations, different ground motion intensities. And the case on the left and the right, again, low shaking, very low damage everywhere, high shaking, high damage. You look at the case in the middle, and we're imagining that those bridges that are inside that circle, maybe those are bridges that are on one set of highway link. And now if the question is, what's not just the damage to a bridge, but is that highway link closed? It's kind of a weak link thing. If you have 10 bridges that you're looking at, if any one of those comes up red or say orange, it's going to close that road. And so what we found, for example, as shown on the bottom, is that if you look, depending on which damage states you're considering to be bridge closure, you know, from this scenario, it would be that 84% of them are going to close that roadway link because one or more of the bridges gets identified as being in a highly damaged state. And we could look at another location of, you know, for the same scenario, looking at another location and the same sort of story comes through there. So this really brought to mind the idea that, well, we've correlated the ground motion spatially. Maybe we should do something about correlating the damage in the bridges, recognizing there is variability from bridge to bridge, but if you go along a certain highway segment, all of the bridges on that one segment may tend to look familiar over a region. So the question is, how could we bring in that sort of correlation between bridges and carry that through the fragility functions? And coincidentally, my colleague Jack Baker, working on a project related to functional recovery in buildings, encountered something similar in that when you look at functional recovery of buildings, you have shaking and you get damage to, say, non-structural components or maybe structural components. You might have, 20 columns in a building. And if any one of them is triggered to a higher damage state beyond a threshold, it's going to close the building. So it's sort of the same problem of, there's correlations between those components, so they're not randomly oriented. So Jack and his colleagues here came up with an alternate way to kind of sample these damage fragility functions. And it's really a straightforward process of kind of taking a fragility function, saying, well, that comes from a distribution with a mean and variability. Let's take that variability in that damage function, and for each realization, let's split the variability into what's unique to each individual entity versus ones that are part of one family and ones that are part of a larger family. So you take the total dispersion. Now you got to use some judgment to divide it up between them. And so our idea here, we're just exploring this now, is to imagine that if you have a bridge on a network, that's going to have some portion of the variability. But then if you think that bridge is part of a highway, there's going to be similarity between those bridges, so that's going to be one level of correlation. And then the last level might be that as part of a larger population. Now you could split this variability into as many subcomponents as you dare, depending on what you can infer about the correlations you have. But we're kind of exploring this now as helping answer that question of going beyond bridge damage to looking at kind of roadway network damage. So I see I'm at time, so I'll just sort of wrap up here and make a point too that one of the things we've been working with is one of my jobs these days as co-director of the Sim Center is to use as many SimCenter tools as we can in this, and in the process help refine and improve those tools and these surrogate models to build those into the suite of models that would be available through the SimCenter. All right, I'd like to thank everybody for your attention.